Thanks very much for having me here. I'm really happy to be at AI Monday. I'm Peter, I'm the Managing Director for Orbica Europe, and my talk today is on geospatial artificial intelligence, and I've titled it The Future of Feature Extraction and Classification. I want to introduce our company first, just a couple of slides. And then I will get into the main topic. Orbica, we're founded in 2017 in Christchurch, New Zealand. Has anyone been to New Zealand or from New Zealand? 1, 2, Australia. And then we founded our European office. Went global last year, and I'm heading up that office here in Berlin. We've got a small team, so we're 24 people now, and 24 Orbicans, and what we're doing is digital geography. And so you might have also heard geospatial data, location intelligence, GIS, geographic information systems, all of these types of different terminologies for the same thing, really. What we're trying to do with that is to help people and organizations to have a positive impact and make better decisions through the power of location data and location technology. And I don't know how many people have used a mapping system, GIS, before. So there are a few in the room, but there's some that maybe haven't. So I thought that I would first give a little bit of an introduction about the history of location intelligence. So I found a video, it's 50 years old, and I hope that gives some context about what we do.
To make decisions, we need facts. But we have facts. We have all seen soil maps and census figures. So what's the problem? The problem is not making the surveys. It is trying to read and summarize the results of the surveys. The amount of work involved in handling this data is enormous. Even the simplest operations take hundreds of people. Raw data and statistics have to be cataloged, stored, summarized, before the data can be used to make decisions. The process is painfully slow. It's bad enough when you're handling census data. It's even worse when you have to handle maps. And so much of our land information comes only in maps. Suppose an administrator wants to find out how much good farming land in his province is still undeveloped, and where. He has to compare the maps showing good farming areas with the ones showing present land use. But they are not at the same scale. First, one map must be remade as a transparent overlay at the exact scale of the other map. Checked, retouched, positioned. To measure the area where both factors overlap, he will probably use a dot grid, a method that hasn't changed since the days of ancient Egypt. What if he wants to consider other factors, such as the incomes of the people, crop yields in a certain soil, forestry, wildlife, recreation, climate, census data? To compare two factors over 100 square miles will take one man a whole working day. To compare only 6 basic factors for all of Canada would take 556 people 8 hours a day for 3 years. It would cost $8 million. But we don't have the staff, we don't have the time. More resource data comes in every year, every month, every day.
So we now, this was analog data, right? And the problems with data and extracting value to make better decisions are still there. The challenge is still there. But now we have digital tools and we've got data stored in digital formats. But there's been many surveys that show that a lot of this data is still only stored, that the value is not actually being extracted out of the data. So what we tried to do at Orbica was to come up with a couple of innovative tools where we could focus on extracting more value from geospatial data. We have two tools that we've come up with. One is geospatial artificial intelligence. The second is geospatial business intelligence. And I'm only going to focus on the AI part today. So what we're doing is we're using artificial intelligence and we are using geospatial processes for their analysis of imagery or Earth observation data. Earth observation data is big data, and it's increasing at an exponential rate. So that's all of the images that are taken by drones and satellites and aerial photos. And just to provide some context around that, here's some numbers from 2017. I need to update this, but these are just increases on the right of the number of satellites. So you see that there's nearly a doubling of the number of optical imaging satellites. In total, there's 620 Earth observation satellites. There's been many studies that show that less than 1% of all of that data that's been produced is actually used. So, to give you some context of what this data looks like, this is a single scene in Canterbury, New Zealand, 107 billion pixels. So it's just one scene. So it's and at one time. At one single resolution. So one time that we're looking at is around 15 million pixels individually. And traditional methods, like not the analog ones that we just saw, but even the current digital and remote sensing techniques that are used, don't allow us to really extract all the information in a quick and easy way. So normally, if you take an image like this, it will take you several hours to basically label all of those features. There's many use cases of geospatial data. These are just some of them that I'm going to touch upon today, and I'm going to share some of the results of our AI algorithm, in particular construction progress reporting, urban development, tracking, and environmental change. So this is how our process looks like in a simplified way. So we take imagery inputs, we process those through our AI engine, and we then have a geospatial engine. So the AI engine outputs raster data. Our geospatial engine will then clean that data and create geographic features. The features are then can be put back through the algorithm to improve and retrain. So all the false positives, false negatives go back into the AI engine to improve the algorithm over time. So we'll show you each of those steps. So this is another tile. What we're looking at is just an algorithm trained for building extraction. So on the left you have the raster image, and on the right you have the binary raster output for buildings. But that's not the data that we can use. So we need to then put it through a geoprocessing engine. So that's the thing that takes all those blocks of pixels and vectorizes those into polygon data. And that's stuff that we can actually use in all of our analysis. So here's just some examples of the algorithms and more outputs, and I wanted to just mention some of the different use cases for this type of stuff. So for building outlines, urban planning, consents is a big thing. In New Zealand there's a lot of unconsented buildings and sleep outs that people make. Understanding impervious layers is super important for hydrological modeling, for example. Creating just up-to-date maps is commercial use. I'll touch upon that in a second. This is the same thing for water, so this is looking at environmental change. So for water, it's, these are braided river systems, and they're extremely complex and also really large systems, and because of this, there's their data sets are currently not being updated with really any high frequency at all, only every half a decade or so. But to give you just an example, one of these images, 96 million pixels in this case, can come through and be processed in under 10 seconds with a very similar PC to the one that we just saw in the other talk. Same thing for roads. So you get the idea, there's lots of different features that you can train an AI engine to extract. And this just gives you an idea of the sort of the speed and scale once an algorithm has been trained. So this is on one 1080 Ti. This is inference, so this is a scene of 600 tiles, 1.5 billion pixels approximately, and then transformed from raw imagery into buildings within 30 minutes. This actually is a little experiment we did last week. So one of our business partners in France, in Toulouse, they sent us some imagery, and they said, just test your algorithm on our imagery. So this is a sample output. We didn't retrain the algorithm for the local context. We just put it through, and this is the raw output. We achieved about 80% accuracy with no additional training of the algorithm. I want to offer that you can also go and check these out yourself on our website. If you go to this page, there's a little slider and you can see all types of different data sets and samples. And now I wanted to talk about a different type of machine learning that we look at for actually classifying features. So once we get all those water features, what we actually need to do is actually label what they are: rivers, lakes, ponds, lagoons. And so what we did is we took a labeled data set for New Zealand, trained an algorithm based on certain features. We combined that with a digital elevation model, so that's the heights. And we had pretty high accuracy, so we had what you see in the green is our water features that we've extracted, and there were some problems though, and so that's what I've shown here. So for example, on the left you see a lagoon that's falsely classified as a lake, and on the right you see a canal that's falsely classified as a river. So this is where you bring your domain expertise, your spatial intelligence. So it doesn't take much to see that the lagoons are close to the coast. So we just added a new feature, distance from the coast, and then the algorithm can classify all lagoons correctly. Same thing for a canal. So canals are generally have a lower gradient than rivers, which follow the natural contours of the landscape. So what we did is we added the slope feature to the rivers, and then the algorithms are able to classify those all correctly as well. The final thing I wanted to mention is a project we've been working on in Germany with a company called ThyssenKrupp. I can't show you all of the outputs because of the commercial sensitivity, but what we're looking at is how can we apply artificial intelligence to help monitor progress on building sites. And I'm quite lucky because they actually produced a promotional video for this particular project we were working on, so I'll be able to show you that. And yeah, happy to answer any questions on it afterwards.
At our plant sites, we do have the challenge to report our progress at site on a very regular basis. And this reporting is time consumable, walking around the site, looking at the buildings, checking for the progress. Orbica came up with the most convincing solution that they presented at Beyond Convention.
Their event for us was really amazing. So our CEO came all the way over from New Zealand, and we got to really make connections with large organizations such as ThyssenKrupp. What we're doing is we're taking all of the drone images from construction sites and we're combining them with 3D modeling techniques, plus artificial intelligence to extract all of the details of those buildings. And we're using that to help measure the progress that is made on those construction sites automatically.
We started with a proof of concept. This was finished very successfully. So we have already a first running technical system available.
This is all made possible from Beyond Conventions. Beyond Conventions allowed us as a small startup to start collaborating and working together with a large organization.
So this is my final slide on GeoAI. So this is how we do it. This is our business model behind GeoAI for us. So we take data from anywhere. You've seen some different types of data, aerial, satellite, and drone imagery today. We are agnostic. We don't have any partners that we only work with. We do it as a service. We try to extract value from existing data, and we do this on a global scale. So thank you very much.